Hello, this is Andrea Hendricks. The topic of this video is solving trigonometric equations. While these equations may look very different than what you're used to solving, we're really going to use a lot of algebraic methods to solve these. Sometimes factoring, the quadratic formula, those types of things will be used. You also will need to have your unit circle with you because you need to be able to choose angles whose sine or cosine is given. So let's look at some examples. These are the selected problems from your textbook that you need to worry about. So I have copied these problems. I'm certainly not going to work all of these, but just to give you an idea. The first few problems are to verify that the solution given works in the equation. So that's just a matter of plugging in. So some of these equations we've actually looked at before. So like, for instance, 7 through 12 says to find the solutions in the equation in the interval from 0 to 360 degrees. And in number 7, we're trying to find where sine x is 1/2. So we're using our unit circle, thinking about what values of x have a sine of 1/2. So if you find your unit circle, what values of x have a sine of 1/2? And remember, 1/2 is a y value on the unit circle. Well, that happens when x is equal to 30 degrees. And also in the second quadrant, there's an angle whose sine is 1/2, and that would be 150 degrees. Cosine x equals the square root of 3 over 2, so that's where what? Yeah, where the x value of the point on the unit circle is square root of 3 over 2. Well, that happens, cosine is positive in the first quadrant and the fourth quadrant, so you would have where x is equal to 30 degrees and x is equal to 330 degrees. The next grouping is just to use the radian measure of the angle, not the degree, but it's the same type of thing. Now let's really get into where we have to do some work to solve these equations. So for instance, in number 26, we're trying to solve the equation the square root of 2 sine x plus 1 is equal to 0. Well, anytime you have a variation like this, you want to try to isolate the sine x or cosine x in your problem. So we would first try to solve for sine x. We would have to subtract 1 and then divide through by the square root of 2. So sine x, in this case, is negative 1 over the square root of 2. And our unit circle typically doesn't have this without being rationalized, so that's equivalent to negative square root of 2 over 2. So we're trying to think, what are all the angles whose sine is negative square root of 2 over 2? Notice this time we're not restricted to just within one rotation of the unit circle. So we've got to think about there are solutions as many times as you rotate through the unit circle. So you're going to find answers where you have an answer plus 2n pi, because that's saying that it's that angle plus a full rotation of that angle, 2 rotations of the angle, so it comes back and round to that same point on the unit circle. So sine x, first of all, is negative where? Right, it's negative in the third and fourth quadrants. So where is sine x equal to negative square root of 2 over 2? Well, that would be at what angle? 5 pi over 4 and 7 pi over 4. So we don't just leave our answers as 5 pi over 4 and 7 pi over 4. We also have to put plus 2n pi to indicate not just that angle, but every rotation of that angle. Okay. What about number 32? Let's look at that one. It is cosine x times cosine x minus 1 is equal to 0. Well, this is already factored equal to 0, so we simply will do this. We're going to replace, or set rather, each factor equal to 0. So we have really cosine x equals 0, or cosine x equals 1. So where does cosine x equal 0? Cosine x is equal to 0 at pi over 2 and 3 pi over 2. So we would have where x is equal to pi over 2 and 3 pi over 2 plus all of the rotation, so we would also put plus 2 in pi. Now where's cosine x equal to 1? That is at 0 degrees plus 2 in pi. Now we could rewrite that as just simply 2 in pi if you would like. Okay. Now let's look at some of these other problems that I kind of skipped. 3 cosecant squared x minus 4 equals 0. How would you solve that equation? So we want to try to isolate the cosecant squared x. We can do that by adding 4 and then dividing by 3. And now we have to apply the square root property, which says that cosecant x is equal to plus or minus the square root of 4/3. So that would be really 2 over the square root of 3. It's probably easier to think in terms of sine, so this would tell us that sine x is the reciprocal, so sine x is equal to plus or minus the square root of 3 over 2. Well, where is sine x equal to the square root of 3 over 2? So sine x is equal to the square root of 3 over 2 at pi over 3. And what other angle? Yes, 2 pi over 3. Now, where is sine x equal to negative square root of 3 over 2? Well, that's going to occur in the third and fourth quadrants at 4 pi over 3 and at 5 pi over 3. So not just those angles, but what? Yes, every rotation of those angles. So you'd have plus 2 in pi. Oops. Okay. Now let me go on to some other problems. We now want to find solutions just within one rotation of the unit circle, and you can certainly use your calculator's table to check any of these. Let's continue with some other types of problems. So for this next step, we're going to find solutions just in one rotation of the unit circle. We can certainly use the graphic calculator to check our work. So for instance, number 37 says cosecant squared x minus 2 is equal to 0. Well, we were going to solve for cosecant squared x equals 2. So cosecant of x is equal to plus or minus the square root of 2. Well, again, we don't really think in terms of cosecant, but if we take the reciprocal, that would be sine x is equal to plus or minus 1 over the square root of 2, which is equivalent to plus or minus the square root of 2 over 2. So in the unit circle, we're trying to find values where sine x is positive or negative square root of 2 over 2. And that's going to occur at all of the pi over 4 multiples, excluding the pi over 2 and 3 pi over 2. So you're going to have pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4 for our answers. Now let's look at some that are a little bit different. Number 40, for instance, has 2 sine squared x is equal to 2 plus cosine x. Well, when you have a sine and cosine, what your goal is try to get just one trig function there. So we're going to have to go back to using some of our fundamental identities. We know that sine squared is equivalent to 1 minus cosine squared. So in place of sine squared, we can put 1 minus cosine squared x. and that's equal to 2 plus cosine x. So therefore we get 2 minus 2 cosine squared x is equal to 2 plus cosine x. So now we can rewrite this and write it as what? Well, the idea is to put it on one side opposite from 0 because we have a quadratic term there. So we can add the 2 cosine squared x plus cosine x, but notice our 2's are going to divide out, so they'll add to 0. So now we can factor this. We have a cosine x from each term, so we get 0 equals cosine x times 2 cosine x plus 1. Setting those each equal to 0 gives us cosine x equals 0, so the solutions for that, where is cosine 0 in one rotation of the circle? Well, that is at pi over 2 and 3 pi over 2. Then we have to solve where 2 cosine x is equal to negative 1, or where cosine x is equal to negative 1/2. And that is where's cosine negative 1/2? Right at 2 pi over 3 and one more of those. And if you need to refer to your unit circle, you certainly can. That would be 4 pi over 3. So the solutions for this problem are pi over 2, 3 pi over 2, 2 pi over 3, and 4 pi over 3. Let me show you another problem kind of similar, but it's going to be slightly different. Let's look at number 44. Secant x plus tangent x equals 1. So is there a way we can rewrite secant x plus tangent x? Well, we know secant x is what? 1 over cosine x. Tangent is sine x over cosine x, and that's equal to 1. So we can add those to get 1 plus sine x over cosine x is equal to 1. So if we try to solve this, we're trying to figure out where 1 plus sine x over cosine x minus 1 is equal to 0. Well, we could get a cosine x now let's work number 44. It is secant x plus tangent x is equal to 1. Now, you could convert everything in terms of sine and cosine, but that's really going to take you down a path that will take a lot of time, but you would eventually get to the right solution. Key thing to do sometimes in trig equations is to square each side, and that can help you use some of the Pythagorean identities to simplify the equation. So what I would like to do is let's isolate secant x to be 1 minus tangent x. And now let's square each side and see how that helps us. So we would get secant squared x. If we multiply this out, that would be 1 minus 2 tan x plus tan squared x. But what is secant squared x equal to? Right, that's one of our identities. Secant squared is 1 plus tan squared x. So we have 1 plus tan squared x equals 1 minus 2 tan x plus tan squared x. So some things add out when we subtract from each side. So what we really have is 0 is equal to negative 2 tangent of x. If we divide by negative 2, we get 0 is equal to tangent of x. Well, where is x or tan x equal to 0? Well, that's where sine over cosine is 0, or where sine is 0, that's at 0 in pi. Now, if we stop here, we're actually going to miss our problem. Because do you remember a rule from algebra? When you square each side, you introduce possibly extraneous solutions. So you've got to check these solutions in the original equation to make sure they work. So if we check 0, look at secant of 0 plus tangent of 0, do we get 1? Well, secant of 0 is 1 over cosine of 0, which would be 1 over 1, or 1 plus 0, which is 1, so that checks. But if we check at pi, secant of pi is negative 1 plus 0 would be negative 1, not 1, so that one does not check. So the only solution that we can include is our value of 0. Okay? Now, continue with this process. This one says you want to use the graphing calculator by setting the equation equal to 0, graphing the new equation, and using the 0 or root feature to approximate the x-intercepts of the graph. So we could do that. I would kind of leave this up to you somewhat, because all you're really going to do is enter one side into the calculator. So let me just discuss with you how you could do this. So in number 49, you could say so you can let y1 equal 2 times sine squared plus 3 sine x plus 1. So you're going to enter that into the calculator and graph it, and you're going to use your 0 function to find the zeros on the calculator. Okay? So you're going to see really where the x-intercepts are and use your calculator to approximate those, and those will be the solutions to the equation. If you have any questions on using the calculator, please contact me about that. And that is the same thing that you're going to do for that next group. Now, now we want to solve multiple angle equations. So to do this, you're really going to just have to make a little bit of a replacement. So if we want to think about where a sine of x over 2 equal to 0, first think about where sine is 0. Well, sine is 0 at what? At 0 and at pi. So what that means is that x over 2 has to equal 0, or x over 2 has to equal pi. Now, since we're not restricted to the one rotation of the unit circle, we've also got to consider that x over 2 has to equal 0 plus 2 pi, or 2n pi, or x over 2 is equal to pi plus 2n pi. So now to solve for x, we can multiply by 2 to get x is really equal to 4n pi, or x is equal to what? 2 pi plus 4n pi. So if we get 4n pi or 2 pi plus 4n pi, those would be the solutions that we need for that. Okay, so that's just really an added step. You've got to set, it's called multiple angle because you've got to set the expression inside equal to the values that you really get for the sine or cosine.